All right. So good morning, everyone, and thank you for coming today to our seminar. This is sponsored by the CAE and CMAT departments. And also this week is part of a seminar series from an NSF award that Pranay and I recently got in sustainable infrastructure materials. So it is with great pleasure that I introduce today to you to Dr. Maria Juenger, who is coming to us from the University of Texas at Austin. So she is the LB Preach-Mathers Professor in the Department of Civil, Architectural, and Environmental Engineering. And also she's the Associate Dean for Graduate Education, Transformation in the Graduate School. So if you work on cement, you know Maria, she's an incredibly accomplished scholar, and she has done truly remarkable work on anything that is chemistry and cement. So she has worked on the clinkering process, hydration, deterioration of concrete, and now she's very interested in the sustainable aspect of cementitious materials. She's associate editor of Cement and Concrete Composites, and she's on the editorial boards of both Cements and Concrete Research and ACI Materials Journal. She's a fellow of the American Ceramic Society and a fellow of the American Concrete Institute, and she serves on the board of ACI. She has got pretty much every award under the ACI umbrella. Walter P. Moore, a Junior Faculty Achievement Award, the Young Member Award for Professional Achievement, the Wasson Medal for Materials Research, the Delman L. Bloem Distinguished Service Award, and the Concrete Sustainability Award. Besides, she also got the NSF Career Award. She has so many awards. Very jealous. But okay, so I don't want to take Maria's time, but I want to, welcome Dr. Juenger. And today she's going to tell us why Bill Gates cares about concrete. So Dr. Juenger, thanks for being here, and the floor is yours.
Great, thank you so much. I'm always embarrassed when people read out the awards and things. You have to realize those were accomplished over many years. I've been here at the University of Texas for 19 years now. So they didn't all happen overnight. So I wanted to talk to you a little bit today. You see the catchy title. This idea for this talk came up in the spring when Bill Gates published a book, and people were talking about it. It got a lot of press and it got a lot of discussion among our concrete community. So I wanted to see what the fuss was about. And so I got the book, but also wanted to talk to people in real terms about what the book was trying to tell us and how that fits into our research and what we're interested in doing in the context of concrete materials research. But before we talk about that, I want to tell you a little bit about where I'm from. Sometimes people, especially in international talks, will give a map and show where they are. I'm assuming everyone knows where Texas is. It's huge. But I wanted to tell you a little bit about our graduate program because it's an interesting graduate program. So in civil engineering, we have MS and doctoral programs, and we have about 380 students. So it's a very large program. It's a large university. About half of those are master's students and half are PhD, and they're spread out in 10 different areas. And the area that I'm primarily associated with is this one called Infrastructure Materials Engineering, which is loosely associated with structural engineering and a program we call Mechanics, Uncertainty, and Simulation and Engineering, or MUSE. But we also have this sort of new program called Sustainable Systems that I work with quite a bit in environmental engineering as well. That look a little bit more about sustainability holistically. And so it's a large and diverse graduate program. And in infrastructure materials engineering, I'm just one of a large group of faculty doing research in this area from three of us who study concrete, Professor Ferron, Folliard, and I. And then Amit Bassin and Jorge Protzi work on asphalt. And then we also have quite a bit of collaboration actually, and I'm doing a lot of work right now on oil well cements. And so I'll touch a little bit on that work later, but that's in collaboration with Professor Van Oort in petroleum engineering. And so we have a large group that covers a lot of bases in terms of concrete materials, with my focus, as Luis said, my focus on cement chemistry. Okay, let's talk about Bill Gates. Everybody knows who Bill Gates is, right? He's the co-founder of Microsoft. He's the fourth richest person in the world. We know he's a philanthropist. He's the author of a new book, came out this spring, on climate change. And then the question is, what does he know about concrete, and why should we listen to him? You know, a lot of us are experts in concrete. What does Bill Gates know that we don't know? And the answer to that question is, it's not that he knows more. It's that he has more power. And so from where he's standing. It doesn't matter whether you like his politics or you like his personality or anything like that. He has a lot of power, and he can make people listen on topics like climate change and public health. So we should be listening as a community to what he's saying and use that as a platform to be able to support and promote the work that we do and direct it so that we get public engagement in the types of work that we do with respect to concrete. So we'll come back to what he says, but I want to say what he doesn't say, because there's a lot of press out there in public news outlets. And this example here is from The Guardian. There's a lot of anti-concrete press out there. And it's because it can be shocking. A lot of the impact of concrete on climate change is dramatic, which makes for really good news. You can call it the most destructive material on Earth. It can be catastrophic. There's a lot of big, nasty words you can use. What I will say right now is Bill Gates doesn't use those. And he's not coming at it from an attacking concrete point of view, because he recognizes that if we want to keep people living in a healthy and sustainable way on this planet, we need to provide housing and infrastructure for them. We need to have civilized societies. And frankly, at this point, those societies need building materials, and concrete is a pretty good one to start with. So he recognizes that. He is not on this anti-concrete bandwagon. He's on the bandwagon of how can we keep our society going, but reduce our impact on the planet. And so I wanted to put that in context about the approach that he has. He's not the enemy of concrete. He is a supporter of concrete, coming from that perspective. He also is part of, I would say, this global trend toward carbon neutrality. Microsoft, for example, has gone public with its statement that it will be carbon negative by 2030. And recently there was a request for proposals from Microsoft about sustainable materials and other solutions to help them achieve this goal. Other companies, you can see here on the right, from about a year ago, there's a list of what other companies' targets are with respect to Apple, Alphabet, Amazon, et cetera, whether they have targets for renewable energy, carbon neutrality, or even being carbon negative. So Microsoft is going carbon negative. Carbon neutral isn't enough for them. In conversations with the Portland Cement Association and Global Cement and Concrete Association, they will soon follow with these targets about carbon neutrality or carbon negativity. It's something that's coming, it's trendy, and everybody's jumping on this, I would say, positive bandwagon rather than a negative bandwagon. I'm going to throw some statistics at you because I think they're fun. Many of you have seen these statistics before. Whenever I go into a talk that's about cement and concrete, people throw the same numbers at me and I go, oh yeah, I already know this, just keep going. But I'm throwing them at you because I'm picking the ones that I think are the most interesting and showing you those. So a lot of people talk about the amount of cement and concrete used globally. What I think is interesting is the people and the work in the literature that have put it in context. So this figure on the left, the black open circles is population growth. So you can see that right axis for population. The blue is cement and the orange is steel. So what this is telling us is that cement production is outpacing population growth. That I think is interesting, right? So it's not just how much do we make, but how is it relative to another metric that we can see in our world. The other thing, the one on the right, I think is interesting because it basically is telling us that, okay, sorry, I get distracted when the microphones go off. The one on the right is interesting is that the amount of cement that we consume is higher than human food consumption. So you think about it that way. We make more cement than food. So not only is it outpacing our population growth, we're actually making more cement than food. It'd be great if we could eat cement, but no. That's the one thing you can't do with it. You can make clothes, you can make buildings, you can make whatever you want, you just can't eat it. All right. I was in I stole this, I actually did like a snipping screenshot during a presentation this week because I thought this slide was interesting, and then yesterday threw it into my presentation. Okay, so you can even see that it says viewing Joe's applications. It was stolen from a WebEx talk. This is a slide that Joe King from ARPA-E used in a grantees conference from ARPA-E this week. And it's carbon emissions, CO2 emissions for various products with cement circled. But what I think is interesting about this is on a per kilogram basis, food actually produces more CO2. Food production produces more CO2 than cement. We just make more cement than food. So the reason it's a target of this anti-concrete bandwagon is because we make more of it than we make food. But this red meat, poultry, even some of the produce is producing more food per kilogram than cement does. So I found that interesting, and so I stole it. Another type of statistic that people show is how much energy it takes to make cement. The numbers are here, they're here for you. What I want to point out is this number of, in a cement kiln, when you use heat that's usually from the burning of fossil fuels to create a temperature that's somewhere between 1400, 1500 degrees C, we can't get here yet with solar or wind power. So it takes a lot of energy, but at the moment we cannot use renewables to get there. So that, I think, is an important point to note about cement. We're still burning something at this point to get there, and we can't move to this concept of using solar or wind to make it more friendly yet. Another statistic that people like to throw around is, and I love this one actually, if the cement industry were a country, it would be the third largest emitter in the world behind China and the US. More than fuel, not far behind global agriculture. I love that. I also tell people that Texas, if it were a country, would have one of the top 10 GDPs in the world. It's ahead of Canada and Korea. So in terms of context, these types of numbers of ranking countries have a high impact, right? So it would be like a country. The interesting thing about that is part of it, this thermal emissions part of this equation is what comes from burning the fossil fuels. But we have another problem. We have thermal emissions from the burning of fossil fuels, but we also have what this one's calling it process emissions. I prefer to call it chemical emissions that happen when we put limestone, which is calcium carbonate, into our cement kilns. We release CO2 in that process, and we need to have that CO2, or we need to have that calcium carbonate because we need the chemical phases like C3S, the Ca3SiO5 in our cement to make it react with water and gain strength. But CO2 is a byproduct of that chemical process that is hard to get rid of. So we're getting bad CO2 from the burning of fossil fuels and from the chemistry of the system. So there's two approaches or two problems there. So the industry several years ago got together and said, okay, we've got these two problems. We've got the burning of fossil fuels that's a problem in terms of heat, of energy and CO2 emissions. And then we have the problem of the chemistry of the system, that in order to make a cement that reacts with water, we need a lot of calcium, which comes from limestone, which when heated releases CO2. So they said, what can we do about this problem to reduce CO2 emissions? And they came up with these, what I'll say, 4 levers. The 5th one has been added recently. So these original 4 levers for change. And you can see the organizations that worked on this, their symbols on the bottom. The first one is just making things more efficient. Can you change the equipment in the cement plant and make it more efficient? The second one is, can we use alternative fuels? So do we have to be burning fossil fuels, or can we use something else? And I'm dividing that into equipment. If you're burning something else, you need different equipment to burn it. And you also need to change your manufacturing process. So I'm defining it as equipment changes and the way you manufacture and process the system. The third has to do with the chemistry of the system. And it's what we call clinker substitution. So clinker is what comes out of the cement kiln. And if we substitute that cement with something else, we can reduce CO2 emissions because we're using less cement. So really what this is a material change. We're using less cement. And so we can substitute it with either a completely alternative cement, or we can substitute it with what we call a supplementary cementitious material, which is a partial substitute of cement. So that's really a material change, changing the chemistry of the system altogether to reduce cement use. The fourth is what's called carbon capture and storage. And so this is done not just in the cement industry, but in the power plants and other places where people are looking at capturing and sequestering carbon. And so that encompasses all of this aspect of equipment, process, and material changes. And I'll get back to that later. The 5th one, which has been discussed more recently, is what we call efficiency of materials use. So if you think about what this really means is it's concrete mixture design at its very basis. So if you take an undergraduate class in concrete mixture design and it tells you to follow the ACI method of concrete mixture design, that is a method. Is it the most efficient method? Probably not. And so then the question is, can we design the proportions of materials in our concrete mixture to use less cement more efficiently? Bill Gates, in his book, focuses on these last two aspects. I'm not going to talk much about the concrete mixture design in this talk, the efficiency of materials use. It's really important, but it's going to be outside of the scope of what I'm going to talk about, but I am going to address some of the other topics here. In those original topics, one of the reasons why Bill Gates is focusing on this concept of carbon capture is because it actually has some of the most power to actually reduce CO2 emissions from the industry. So innovative technologies, including carbon capture, can cumulatively reduce millions of tons of CO2 from the cement industry. This idea of clinker reduction is sort of the second best option of removing CO2 from just a pure volume of CO2 or mass of CO2 reduction. Switching to alternative fuels is next, and then this thermal and energy and efficiency and other electric changes are lower, but they're really small compared to the others. And so in this particular talk, I'm going to focus on the middle three topics. The thermal and electric efficiency is useful, but it has a really small impact. The efficiency of material use is really, really useful, but it's out of the side of the scope of what I'm going to talk about here. I'm going to talk about the middle three, which have the most power, really, to change our industry. And the one in bold is the one I'm going to talk about the most, and I'll tell you why. Not just because it's my favorite, but it's because if we think about what we have the power to do as civil engineers, I talk about this quite a bit in my classes when we talk about steel versus concrete. When I teach my undergraduate students about steel, I tell them steel is great and here's how it works. And I tell you this so that when you design something made out of steel, you make a good and reasonable choice of which steel to use, but you do not make the steel. On the other hand, concrete, civil engineers design and make the concrete. It's our job to design and make concrete. It is not our job to make steel. The metallurgists make the steel, we use it. The same thing is true when you look at these levers. From an alternative fuel perspective, this isn't really a topic that falls under the purview of civil engineers. It's much more of an industrial, mechanical, chemical engineer type thing. It's about changing the fuel you burn in a process. So I'll talk about it, but it's not something that we really can do research on. We can do research on the impact of what happens when you've done it on the material, but we don't do research on the fuel changing itself. The same with certain parts of the carbon capture and storage equation. Civil engineers use the material that comes out. We're not actually in the business of designing the mechanical systems and chemical systems that do the carbon capture and sequestration. We can examine the impact, but not the process itself. Whereas this concept of clinker substitution, this is all us. It lands completely in our laps as to how to design our materials and use and choose new materials that allow us to use less cement in our concrete systems that then therefore reduce CO2 impact. So this is in bold, not just because I like it and do research in this area, but this is the one topic that we have the most power over, and five. But again, I don't have a lot to say in that area of my own work, so that's why I'm not talking about it. Okay, so let's talk briefly about alternative fuels, just so you have a good sense of what's happening here and what people mean. So in terms of alternative fuels, people generally burn coal, oil, or gas to fire the cement kiln to that 1450-ish temperature that's necessary. There's a lot of other materials you can use. Sewage sludge, animal bone meal, used tires, solvents, plastics. There's a lot of waste materials people are burning, but if you look at this entire list, all of it is still burning, which means there's still emissions associated with it. They may be byproducts of other industries, but they're still burning. One of the things I want to mention about that is you are changing the equation with respect to CO2 emissions for sure, but there are side effects of this. So I mentioned I can't study what's going to happen in a cement plant to the temperature when when you burn a different fuel. But for example, for many years, this concept of animal bone meal, people have been using animal bone meal in cement kilns and burning this waste animal products for decades. One of the things they noticed pretty early on, which was really interesting, is that when you burn any waste, but in the particular original studies, when you burned a bone meal, there was a lot of phosphorus in the bone meal that then would be released from the burning of it that would get into the cement itself. So we can study not what the materials are that you would burn, but we can understand the impact of burning that material on the cement itself and how that affects its performance. Because of the way the system is designed in a cement kiln, particulate matter can rise up from the combustion chamber and mix itself in with the cement, which is interesting. So also, in January this past year, so 2021, in January, I was preparing another talk and I was looking at these types of concepts and I did a bunch of Google searches. And so you know how I said you can't really use solar or wind, it doesn't have high enough energy? Turns out people are actually looking at this, which is super, super cool. So there may be ways to actually take advantage of solar energy and these solar fuel technologies to actually produce enough heat to fire a cement kiln. And so CEMEX, in this press release from 2020, is saying that they're looking into this. So it may be possible, just not with the technology that we commonly have and commonly use today. About a month ago, we installed solar panels on our roof. I'm telling you, those solar panels will charge our electric cars and use our excessive air conditioning that we use in Austin, Texas. They're doing a really good job at that. They are completely not capable and not the right technology to take a cement kiln to 1450 degrees. We're not there yet. Okay, let's talk about, I'm going to go dive a little deeply now into this concept of clinker substitution, since this is the area that many of us work on in concrete materials. So I'm dividing clinker substitution into two different types of concepts. There's a concept of still use Portland cement, but replace a portion of it so you use less of it. And then there's a concept of forget Portland cement, use something else entirely. So what we're calling these is 3A, since we had 1, 2, 3, 4, 5 levers. This is lever number 3. 3A is a clinker substitution using a supplementary cementitious material, and that's the technical term for it. And then we'll talk about 3B, which is get rid of, don't use Portland cement, use something else entirely. So basically 100% clinker substitution. In this case, we're talking about 10, 20, 30, 40, 50% of the cement being replaced. Okay, so admittedly, using supplementary cementitious materials is not a new idea. This has been done for decades, and more than 60% of ready-mix concrete in the US uses this already. So in terms of impact on how we make and produce our concrete and how our concrete performs, we're already doing this. This is already part of our strategy. Originally, it was a strategy to reduce money or to reduce cost and to improve concrete durability. But now people are targeting the impact of this on sustainability. So this strategy is not new. It's already being used. The research challenges there are multiple, but one of them is that the supply chain is changing rapidly for these types of materials. So that's one research challenge. Another is, how do you take that more than 60% number and turn it into 100%? How do you get better adoption of these types of technologies? Another research question is, how do you get more in there? So in terms of material design efficiency, how can you improve the amount that's in there? When we're talking about supplementary cementitious materials, this particular chart on the right is an example of the types of materials we can use, and we do use. So Portland cement is on there as how much of this we use per year in million tons per year. And then we have other materials that are on this chart, such as fly ash, slag, natural pozzolans, calcined clay, etc. So we have a lot of different materials to choose from. The reason we're using these to replace a portion of our Portland cement clinker is because they inherently have lower embodied CO2. So this particular chart shows here's cement here in terms of embodied CO2 on the y-axis and embodied energy on the x-axis. And so you can see where it falls here compared to other materials. If we're using things like supplementary cementitious materials, they fall into this sort of yellowish brown, I don't know what the technical term for that color is, yellowish brown oval. These are the other materials we use, and you can see that many of the materials that we're using have a lower embodied, as supplementary cementitious materials, have a lower embodied CO2 and embodied energy. So that's why we're using them. The question then comes, can we push it even further down the line? Can we start using gypsum? Can we start using asphalt? Can we start using other things, right? The answer is you have to use something that is chemically compatible with the system that gives you the performance that you want. You're trying not to just dilute your cement. That's easy enough to do. You can dilute the cement with anything. What we're doing here is we're trying to put something in our system that actually is chemically reactive so that we improve the properties of our system, or at least keep the status quo. So we can't just look at anything. And what are we looking for? So in terms of what we're looking for, there's several qualities that we're looking for. We're looking for a material that's primarily glassy. We're looking for a material that either comes as a fine powder from its source or can be ground into a fine powder. So it kind of looks like cement. And we're looking from a chemical perspective for something that has a high silica content and alumina content. And the reason is we want it to have a high surface area so it can dissolve in our cementitious pore solution. And we want so we want it to be fine and have a high surface area. And we want it to have a high amorphous content so that it can dissolve in our cement pore solution as well. So we want something that's soluble, that will be reactive. And the reason we want this is we want it to react in what we call this pozzolanic reaction with calcium hydroxide that forms from our Portland cement, so that it forms this calcium silicate hydrate phase that forms, that gives us strength and durability in our concrete. And we want all of this at a low cost. So we want everything. And so the question is, how do we get that? We want everything, and we also want it to be low energy, low CO2. So it's a lot to ask for in a material. Historically, in the US in particular, fly ash met all of those criteria. So fly ash is a byproduct from coal, from burning coal for power. So it met all of those criteria. It was an amorphous material, it was mostly glassy, it was high in silica and alumina. It already came as a fine powder, you didn't need to grind it. It was a byproduct from another industry. So in terms of embodied CO2 and embodied energy, it was doing pretty well from that. But we all know that burning coal for power is on its way out. And so this particular plot more or less shows that of the decrease in coal burning power in countries projected into the future. So we need to look for other materials to meet the demand. If we want to get from 60% of our concrete uses supplementary cementitious materials to 100%, and we want to use more of it, we need to be able to look and identify look for and identify other materials that meet that those needs. What I would say is, in this search, what we're looking for is performance. How good is the material? And what I will say is, we don't need it to be great, we need it to be just good enough. And I'll get back to that. Cost. We're not looking for something at this point in the technical market, we're not looking for something that's super cheap. Fly ash was cheap because it was a waste product historically. We're looking for something that is more or less the cost of cement, maybe slightly higher, slightly lower, but at least it's going to be cheaper than carbon capture. So we need to kind of temper our expectations for these types of materials. One of the really good candidates of materials that we can use as a supplementary cementitious materials are natural pozzolans. These are volcanic materials like pumice and perlite, volcanic ashes, zeolites, similar in many ways to what the Romans used in their concrete mixtures. And then sedimentary pozzolans, so calcined clays and shales that don't simply have to be just quarried, but need to be heated, or what we call calcined at a high temperature in addition to being quarried. And one of the interesting things about these materials is that Whereas fly ash is decreasing in availability, the current commercial availability of these natural pozzolans is actually increasing. But because you need, in many cases, a volcano somewhere nearby geographically to have deposited the volcanic minerals, they can be really limited geographically, but not in all cases. What I'm particularly interested in looking at is, and we're going to talk about some case studies, is how can we take these materials that are inherently have lower CO2 and embodied energy than a Portland cement because they're simply quarried or heated to a lower temperature. How can we take these materials and combine them with our interest in using waste products like we did for a fly ash as well? And then how can we blend them and optimize them to make them meet our expectations in terms of having a relatively low cost and having just good enough performance? And so I'm going to talk about that with a few case studies. This picture on the right is a picture of a pumice mine that we visited before the pandemic in 2019. So I put that there because I thought it was just really cool. All right. So when we're looking at finding supplementary cementitious materials, our gold standard is fly ash. But what's great about having fly ash as a gold standard is it's not actually a great material. It's kind of a mediocre performer. In terms of reactivity, it's only 20 to 40% reactive. And the reactivity compared to many other materials that we are interested in that is as supplementary cementitious materials is more or less average to low. So when we're talking about a substitute for something, at least we're not aiming really high. We're aiming for something that's relatively mediocre, which is good to know. So if we're assuming that fly ash is a reference SCM, a reference supplementary cementitious material, we don't really need great performance. We need just good enough performance. And actually, it's better from reducing the amount of cement that you have in your system to use a high amount of mediocre material than a very small amount of really good material. So in terms of balancing and materials design, it makes a lot of sense. And this opens up the opportunities for using what we would say less desirable natural pozzolans or blends of materials to kind of target a performance and cost perspective. So designing the system to be average. It's really counterintuitive. You usually want to design something to be optimal. We want to design it to be so that we can use it cheaply, abundantly, and get okay performance out of it. So the first example I want to give of a case study here is what I would call impure, or what we're calling impure pumice. So pumice is a great natural pozzolan. It's also used for a lot of other industries, commercial industries. And most commercial industries want a more pure pumice. So what you see on the left is in this bucket is kind of a white, more pure pumice. And typically what happens when you have a quarry and you're quarrying material, you have material at the top that's mixed with other minerals. It may not be as pretty and it's not as compositionally pure. And so you get something that, in this case, the manufacturer is calling tan. So the tan pumice. They're both pretty good, high in silica and alumina, very high in silica and alumina. So they meet that criteria that we have. The pure pumice is really amorphous. The overburdened pumice is less so. The tan pumice is less so. And so what we're interested in knowing is for the concrete industry, is the tan pumice, the stuff they're really just throwing away, can we use that? Can we use your garbage and get just as good of a performance or close enough to the more pure material that you're selling to other industries? And the answer is, I'm going to show you a couple of just quick examples of data. This particular test is a reactivity test that's now standardized in ASTM C1897, and we call it the R3 test. In this particular plot, I'm going to show you this plot a few times with different circles on it, looking at different materials. If we look at something that's inert, like a quartz or titanium dioxide, this value here is low. If we look at something like a fly ash here, this value is medium. If we look at a pumice, the pure pumice, the PP, or the impure pumice, this overburdened pumice, the PI, their reactivity in this particular test method is about the same as fly ash. So they both actually meet our goal of being just as good as fly ash. And yet the impure one is a waste product, just like fly ash as well. In terms of compressive strength, which is another metric people are interested in, these are 28-day strength values. This black one is on a 100% relative strength compared to Portland cement, which is in the black. And these materials, these overburden pumice material, has the same compressive strength as a Portland cement. So in terms of being able to replace fly ash with this, be able to make concrete with this, it's a good material. You don't need to use the more pure one. Another just example test of what people are looking for when they're looking at supplementary cementitious materials is they're interested in looking at how they help concrete durability. So in this particular example, for alkali silica reaction shown here, it's a reaction that causes expansion and cracking in concrete. In this Portland cement, you're getting a high expansion on your y-axis over time. But when you replace Portland cement with pumice, fly ash, they all reduce expansion. So the pumices perform quite similarly to the fly ash, even the overburden material. So it proves to you that the concrete industry can take the rejects from other industries quite easily and don't have to use their more pure products. Another example similarly is clay. So clay is abundant around the world, and typically in concrete mixtures, we've used a very purified form of kaolinite clay that's been heated called metacalein. We typically use it in really small amounts because it negatively impacts the workability and can have a really, really high cost. So we're using it in very, very tiny amounts. But there's an increased interest in using clays at greater amounts as substitutes for fly ash, in which case you can start looking at clays that are less pure and what the impacts of those materials are in the system. So in this particular study, we're comparing a really pure metacalein clay, a 99%, with one that's more like 77% amorphous and has contaminants in it. And what you can see, if we look at reactivity, the reactivity of both is significantly higher than the fly ash. The reactivity of the less pure material is less than the really good one, but since it's better than the fly ash, it's still suitable for our concrete mixtures. And in terms of compressive strength, the strength is great as well. Reducing the quality doesn't necessarily make it a worse product for our concrete mixtures, and in some cases could actually make it better. So one of the problems with metacalein is that typically, as I mentioned, you use it in really small amounts because it's really expensive and because it really increases the water demand of the concrete mixture. So it makes it really stiff and hard to mix and sticky. So people use it in really small amounts, let's say 10%. What we found that when you use a less pure calcined clay, you can get workability similar to other pozzolans. So in this particular example, these are rheology plots of shear stress versus shear rate, where the slope gives you some indication of viscosity. And so the black line is just a Portland cement mixture, and the metacalein is this green one, which has a slightly higher viscosity, but still within what's reasonable for a concrete mixture, whereas the metacalein, pure metacalein, which I don't have on this plot, but we do have data for, is a much, much higher viscosity mixture. Sorry, lower viscosity, higher. I always get mixed up with that. I have to think about syrup. Yeah. Okay. The other thing that's interesting is if you start using these less pure materials, again, this is counterintuitive. You think you want to use the best, but there's so much literature and data out there that says, let's aim for mediocre. This is an example from a study in Switzerland from 2018 that basically says, as you increase the kaolinite content of a calcined clay, so you increase that amorphous content effectively, you actually decrease the reactivity of the cement itself. So they're competing. So really what you want is a calcined clay that's about 50 to 60% amorphous or 50 to 60% kaolinite, because you can get the optimal reactivity of your Portland cement and yet use a cheaper, better, just as good for your properties calcined clay. So there's a lot of really interesting material optimization that's happening here. Okay, my third case study, which is pretty short, I promise, is kind of a case study, and be careful what you ask for. So we really are interested in looking at byproduct materials for our supplementary cementitious materials because we want things that are low cost. So an example of this in the US, most of the shingles that are used on roofs in the US are these, what they call asphalt composite shingles, where you have an asphalt binder and you have really uniformly graded small aggregate that are blended with this asphalt binder, put on a sheet of paper and tacked onto the roof. So I think in Miami, you might have more clay tile roofs and it might be much nicer. But the rest of us end up with these composite asphalt shingles. So these fines, it's interesting, like we know from making concrete aggregates, if we're quarrying, say, a limestone aggregate, we know that we have to quarry it and crush it. And then in the process of crushing, we end up with a lot of fine material that we consider as waste. The same for this sort of process, they're looking for a specific particle size range. So anything smaller than that is a waste of a byproduct of their industry. What's interesting about those is some of those particular aggregates have silica and alumina in them. And so they could presumably be really good supplementary cementitious materials. If you start looking at the 28-day strength of, in this case, a mortar made with those materials, this black one here is the Portland cement. These materials, NM1, 2, 3, and 4, those are the byproduct asphalt shingle aggregates ground or that are very fine in the same particle size as Portland cement. The P1 and P2 here are actually our pumices that we looked at earlier. So if you look at the 28-day strength, they look great. You think, oh, we've got a really great source of supplementary cementitious materials as a byproduct of these industries. It seems to not affect 28-day strength at all. However, if you start looking at later strengths, it tells another story and then starts to raise suspicion. If you look at the Portland cement, you have a 28-day strength here of a little over 6,000 PSI, or let's say 42 megapascals. And the pumice is even higher, the pure pumice. The impure pumice is the same as the Portland cement, but you start looking at these others and they never caught up. So it starts to raise suspicion. They're not behaving like the pumices. They're not behaving like a supplementary cementitious material. They're behaving a lot more like the impure quartz. And so the question is, why? If we look at reactivity tests, this ASTM C1897 R3 type test, it starts to tell some interesting stories. We have a quartz, which is pretty low reactivity in this test method, which it should be. We have the pumices, and then we have these other minerals, which are kind of low on this scale. They're not as low as the quartz, but they're pretty low. And so you start to say, well, what is it with these materials? They're fine grained. They have silica and alumina. What's the other part that we need? The other part that we need is we need them to be soluble. We need them to be glassy. And if you look at the X-ray diffraction data from these types of roofing shingles, if you have a pumice, you see you get this little glassy hump here. So you have some crystalline phases in there, but you have this little hump that indicates you have amorphous material. In these roofing shingles, there's no amorphous hump. There's no glass. So we have to be careful when looking at these data and looking at these materials to really make sure that all of our criteria are satisfied. They have to be amorphous or at least soluble, fine-grained, have silica and alumina, and they have to be reactive. So we have to be a little careful in our search as well. So that's my, my warning sign. Okay, I'm gonna move on and talk about clinker substitution and carbon sequestration quickly. I used to do a lot of work on alternative cements. It was a lot of fun. It was great to do research on these. I did quite a bit of work on calcium sulfoaluminate baelite cements. I am still doing some work on geopolymers, which are alkali activated fly ashes and other materials. And there's many other ones of these systems that are magnesium based and otherwise. I included this picture on the right because most of the work that I do is really small. It's chemistry. Everything's in the lab. We actually made this geopolymer bench for a hotel as a project for a construction company to make an alkali activated fly ash bench. And we were really excited about it. And then they showed us a picture of it in place, and it looks like they put it in the smoking area near the exit of the hotel. I need to go and look for it. I don't even know if it's still there. It was really kind of sad, but that's the one, like the biggest thing I've ever made out of it, alkali activated material. right now we're focusing our alkali activated material works for oil well cements because they actually work really well in some of those applications. So I'm still working on those systems in that context. I do want to point out that companies are still working on these alternative cements. For example, Cemex has made a press announcement in 2020 about using a geopolymer system and selling it commercially. So this is still a direction that many companies are working in. The problem is when you're thinking about how to implement things into the concrete industry, we really want to keep the industry going exactly as it is for now. So our primary goal, and something that I feel strongly about, is it's really easy to implement something if everybody can continue business as usual. So supplementary cementitious materials are really attractive as a way to reduce CO2 emissions from the concrete system because they allow us to make concrete that is identical to the concrete we're used to making and provides good performance. And so it's easier to implement into the construction industry, which tends to be pretty slow and conservative. These materials are great. They may be really, really powerful many years down the line. They're really difficult to implement into our building codes and other construction practices because people are resistant to using them. And so I think they're a really good area to be doing research in. I think that your perspective has to be long-term, or at least either smaller projects or long-term. We'll get there in terms of wider spread implementation, but it's a much longer path to get there. There are some really interesting materials that are alternative cements that actually combine the concept of carbon sequestration with the concept of an alternative cement. These are two company examples here that shown on the left and right, where you actually use CO2 in the cementation and mineralization process. And so we can combine the concept of carbon capture with an alternative cement and make a building material that way. So that's a lot that is interesting as well. But most people, including Bill Gates, you thought I lost the Bill Gates thread, but I'm back. Most people, including Bill Gates, when they think about carbon sequestration and carbon capture, they're thinking about technologies that happen in the industrial process. And the cement industry is actually doing some of this already. So there are pilot plants in Norway, Taiwan, and in the EU that are actually changing the way their cement plants work to actually capture CO2 and put it in solution, or put it in, for example, creating a limestone or something from that as well. And so these are three examples. You can look them up and get more details on them later, but it's happening. It's a process that has gone from design to actual pilot scale and could potentially go into large scale implementation. What this plot shows here, though, is it's expensive. So these processes cost a significant amount of money per ton of CO2 captured. Okay, let's get back to Bill Gates. I'm not going to go into the technical details of this. So Bill Gates recognizes this. If you read the chapter in his book, he has a table that I basically cut and pasted from his chapter of the book and put right here. So this is taken directly from the book. And he, in that chapter, doesn't just focus on cement. He looks at plastic production and steel production as well, and looks at what's the impact economically of actually implementing carbon capture. So carbon capture is expensive. It's changing a cement plant to operate in a different way. If we look at cement and we look at implementing carbon capture, we're doubling or tripling the price of cement. Somebody's got to have to pay for this, right? Bill Gates argues that the cost of the cement is going to go up, but it gets passed on to companies, not individual consumers, since it's something that's used by larger scale companies or organizations rather than consumers. I would argue it gets passed on to the consumer anyway through higher taxes and other things. So somebody's going to have to pay for this. He thinks that it has to come from government subsidies or other types of policies and incentives, and argues that it's not about making a choice of buying cement number one that's cheaper and emits CO2, or cement number 2 that's more expensive and has used carbon capture, he argues that everybody has to sell the same product and everybody has to use carbon capture. And I believe that's where the industry is going to go. That it's going to be an all or nothing thing. It may not hit the US for quite a while, but it's going to hit Europe first and other countries that are more engaged in reducing CO2 emissions, but that the technologies, once they're developed, are going to become widespread. We're going to see an increase in cost. I personally would argue that that's okay. And the reason I would argue that it's okay is we're spending more money to continue business as usual. Just like using supplementary cementitious materials gives us a concrete that looks just like and acts just like the concrete we're used to using, carbon capture gives us that power as well. It allows other technologies, such as alternative cements, to catch up and to gain acceptance, but it's something we can do in the very near term to allow us to continue building and constructing our concrete the way we want it to be without having to make changes to the building code or what we consider acceptable for safety and durability, long-term durability. So it's incredibly powerful. We're just going to have to pay more for it. So I would say at the end of reading Bill Gates's chapter, I was a convert. I became a convert to carbon capture and to spending more money and more of our industry's direction on this, as well as the supplementary cementitious materials, because it gives us the power to do something right now and let the other more advanced technologies catch up. So, you know, in conclusion, we really need to use cement and concrete. They're really important for our development of civilizations in the world, right? We can't just stop building and repairing infrastructure, and Bill Gates agrees with that. We need to use supplementary cementitious materials, lower the cementitious material content in concrete, design structures more efficiently to use less concrete, and then use carbon capture in the very near future and alternative cements and fuels as those technologies develop. So I want to thank you for your attention, and I will definitely take questions. I see there's some things in the chat as well. I want to thank the Texas Department of Transportation for, I think, 8 years of funding to work on supplementary cementitious materials, and the students who've worked on those projects, as well as collaborators and other organizations that have given us materials and support over the years. So thank you.